Okay, the length of the largest subinterval the length of the largest subinterval is called the mesh of P, and is denoted by this mesh is denoted by mod of P. Okay, so mod of P means the length of the largest subinterval. That's we have mod of P is equal to maximum of these lengths. It's x1 minus x0, x2 minus x1, so on up to then it's xn minus xn minus 1. So it's a maximum of these lengths. That's called the mesh of the partition P. Also if P and Q are two partitions of the closed interval a b, such that this P is subset of Q, then we say that Q is refinement of P. Then we say that Q is refinement. Q is refinement of P, or Q is finer than P, or Q is finer than P. Okay, if the partition P is subset of the partition Q, then we say this partition Q is refinement of the partition P, or we can say Q is finer than P. That's the definition of the refinement of a partition. So now let's do the following notations for a partition P, for a partition P which is equal to A equal to x0, x1, so on up to xn, which is equal to B. For a partition P, we have the following notations. Let's take these notations. Let small mi is equal to the infimum of f of x over the ith subinterval. It's the infimum of f of x, where this xi minus 1 less or equal to x, less or equal to I. Okay, so this x belongs to this ith subinterval xi minus 1 to xi. That's a small mi. It is the infimum of this function f, and the capital F mi, it's equal to the supremum of this you have done already in basic course also, f of x, such that xi minus 1 less or equal to x, less or equal to xi, less or equal to xi. Okay, this is true for all I equal to 1, 2 up to n. So that means m1 is the infimum of the function f(x) over the interval x0 to x1. m2, small m2, is the infimum of the function fx over the interval x1 to x2, and so on and so forth. So in a similar manner, this capital M1, it is the supremum of f of x over the interval x0 to x1, and capital M2, it is the supremum of f of x over the interval x1 to x2, and so on and so forth. Then we define lower sum. Then the lower sum, then the lower sum, it's this with respect to the partition P, with respect to P is denoted by, it's denoted by S lower star Fp, and is defined by S lower star Fp is equal to, it's equal to the summation I runs from 1 to n small mi into xi minus 1, and the upper sum is denoted by this is the lower sum, and we have upper sum also, and this the upper sum with respect to the partition P is a function f, where f is a function, it's a bounded function from AB to R. Sorry, I don't have mentioned it here. It's a function, f is a bounded function from the closed interval AB to R, and the upper sum with respect to the partition P of the function f is denoted by, so f is bounded function, okay, is denoted by S upper star Fp, and is defined by S upper star Fp is equal to summation I runs from 1 to n capital Mi into xi minus 1. Okay, that's the upper sum and the lower sum of the partition P with respect to the partition P of the function f. Since this Mi is always less or equal to capital Mi, because Mi is the infimum of fx over the ith subinterval, and capital Mi is the supremum of the function fx over the same subinterval. So infimum is always less or equal to supremum. This is true for all I equal to 1, 2 up to n. So this implies Mi times any positive number. Let's take this positive number xi minus 1, because xi minus 1 is less than xi. So this is always less or equal to capital Mi times xi minus 1. And this is true for all I. It's true for all I equal to 1, 2 up to n. And let's add these numbers. Okay, there are n numbers actually, and this inequality holds for each number. So we can add these numbers, and this inequality is preserved under that addition. So this implies the summation I runs from 1 to n capital Mi into xi minus 1 is less or equal to summation I runs from 1 to n capital Mi, here it's a small mi, xi minus 1. But this one, this is the lower sum, it's S lower star Fp is less or equal to S upper star Fp. So for any particular partition, lower sum is less or equal to the upper sum with respect to that partition. And not only this, if we have any two partitions P and Q, lower sum with respect to the one partition is always less or equal to the upper sum with respect to the any other partition. So this inequality does not depend on any particular partition. This is true for any two partitions P and Q. If you take any partition P and Q, S star S lower star Fp is always less or equal to S upper star Fq. But for this, we first need to do the following. Let's I will keep this exercise for you. Let P and Q be two partitions be two partitions on the closed interval a b such that this p is subset of q. Okay, then show that lower sums increase and the upper sums will decrease. This you have already done in basic course also. Then show that I will not prove it here. Then show that this the lower sum will decrease when we take the refinement of the partition. Okay, but the upper sum will this is less or equal to, sorry, this is not a greater or equal to, this is less or equal to, okay, is less or equal to, and the upper sum will decrease. Upper sum fp is greater or equal to, upper sum will decrease. Okay, it will not increase, but this will increase under refinement. S star f q. Okay, this is q here, this is q here. So next exercise, for any two partitions, for any two partitions p and q of a b, show that this lower sum is always less or equal to the upper sum. So hit use previous exercise, use previous exercise and choose a common reference and choose p dash, which is equal to p union q, the common refinement of p and q. Common refinement of p and q. This is the hint for this exercise. I'll use previous exercise and choose the common refinement of p and q. This common refinement, obviously it's a refinement of p and q because it contains p as well as q. That's why it's called the common refinement of p and q. Okay, so next we define, so let's see this. Next we define let's define this. Let this is called the lower Riemann integral of the function f. It's equal to the supremum with respect to the partition. P belongs to the partition of AB. You are varying the partitions now and you are getting different lower sums. Function is fixed. Okay, so if you vary the partition, you will get the different lower sum, and you are taking the supremum of that set of the lower sums. That will be denoted by I lower star f. Let I star is equal to this, and this I upper star of f, it's equal to the infimum of the p belongs to the partition of a b of the upper sums. Okay, this lower star and upper star, I upper star of f, are called the lower Riemann integral. Lower Riemann integral of f, and upper Riemann integral of f. So one can easily verify that. This is also as an exercise for you. One can easily verify that this lower Riemann integral of f is always less or equal to the upper Riemann integral of f. Okay. Now we have a definition of Riemann integrable function. Okay. If this lower Riemann integral is equal to the upper Riemann integral of f, then f is said to be Riemann integrable. Then f is said to be Riemann integrable over AB, and we write it as we write this f belongs to R of AB. R of AB means the collection of all Riemann integrable functions. It's a collection of all Riemann integrable functions over the interval AB. Okay, so it is denoted by this notation, R of AB. F belongs to R of AB. Okay, next we have a following theorem which is very important, and I will also leave it for you, okay, because this you have done in BSc course. A bounded function f from closed interval AB to R. A bounded function f from closed interval AB to R is Riemann integrable. Is Riemann integrable if and only for all epsilon positive. There exists a partition P of A B such that upper sum of f with respect to the partition P minus lower sum of f with respect to the partition. This is always a positive number greater or equal to 0, because this is always greater or equal to this, but this should be less than epsilon. There should exist a partition P with this property. A bounded function f from closed interval AB to R is Riemann integrable over AB if and only for each epsilon positive there exists a partition P of AB such that S star FP minus S star FP, S upper star FP minus S lower star FP is less than epsilon. So proof as an exercise. Okay, proof as an exercise. So proof is very simple. You have to apply the definition of supremum and infimum. Okay. Proof. It's an exercise. Okay. So here use definition of supremum and infimum. Also use common refinement. Okay, common refinement. So that's an exercise for you, and this is the hint for this the exercise. And this theorem is called the Riemann's criteria for Riemann integrable functions. Okay, now we define the another sum that's called the Riemann sum. Now we define another sum that we call the Riemann sum. Okay, so that's the Riemann sum. Riemann sum. Okay. Riemann sum. So what's the Riemann sum? Let's define the Riemann sum. But again, this f is a bounded function, obviously. Let f from a to b, a, b to r be a bounded function. Be a bounded function. And this p, which is equal to a set a equal to x naught, x1, xn, which is equal to b, be a partition of ab, be a partition of the interval a b. This is the partition of interval a b. Now we take the collection of points. Okay, we choose a point t1 in the interval x0 to x1, and we choose a point t2 in the interval x1 to x2. Okay, now let's choose the collection of points. A collection of points, a collection of points, t, which is equal to t1, t2, so on up to tn. This is the collection of points t1, t2 up to tn, where t1 belongs to the first subinterval x0 to x1, t2 belongs to the second subinterval x1 to x2, and so on tn, it belongs to the last subinterval xn minus 1 to xn. Okay, so this is the collection of points. Is said to be a collection of points is said to be a selection of points for p. Is said to be a selection of points. A selection of points is said to be a selection of points for the partition p, for this partition p. Okay, now we define let's define mu sum with respect to this selection of points. Define that I will denote by rft. Okay, rf, it's a function for the function f with respect to the partition p and with respect to this selection of points, because we can choose a different selection of points which have chosen t1 in the interval this x. Now we can choose another point, say we can choose say t1 dash, then we get the different selection of points. Okay, so for this we get the different sum, sum, so that selection of points we will denote by say t dash. So for this selection of points we have the following sum, that's equal to summation I runs from 1 to n f of ti into xi minus xi minus 1. Okay, this is xi here, it's xi. So let me erase it here. Okay, this is not looking good. Okay, let's this is equal to xi minus xi minus 1. This sum R of AB is called the sum R for the function f with respect to the partition p and with respect to this selection of points is called a Riemann sum associated with the partition p, is called a Riemann sum. Let me choose the next page. Is called a Riemann sum, is called a Riemann associated with the partition p, with the partition P. Okay, obviously it also depends upon the selection of points. Now we have following theorem which I will prove here because this theorem is very important for our further investigations. So let's state this theorem first. Okay, it's called Doorbox Theorem. Doorbox, okay, Doorbox Theorem. Let f be a function. Let f be a function from the closed interval a b to r. Okay, it's a bounded function, obviously. Not bounded, it's integrable. Is Riemann integrable. That means upper Riemann integral is same as the lower Riemann integral. Is Riemann integrable. Is Riemann integrable. Okay, is Riemann integrable. And let Pn be a sequence of partitions. Let Pn, that means P1 is the one partition, P2 is another partition, P3 is another partition. So Pn, it's a sequence of be a sequence of partitions. This B Riemann integral, not is sorry, it is here B Riemann integral. Okay, and let Pn be a sequence of partitions. So we are not only one partition, we have a sequence of partitions. Okay, the sequence of partitions of the closed interval AB of the closed interval AB such that the maximum length, the mesh of Pn, or the maximum length mod of Pn, its limit n approach to infinity is equal to 0. We can choose such a partition for any closed interval. It's not too difficult. So that this limit is approaching to 0. Then the conclusion is then this limit n approach to infinity. Limit n approach to infinity, lower sum s lower star Fpn is same as the limit n approach to infinity s upper star Fpn, and it's equal to the Riemann integral. It's equal to integral a to b f of x dx. So this limit is equal to the Riemann integral. F is given to be Riemann integrable function, means the lower Riemann integral is same as the upper Riemann integral. So in particular it shows that in particular if a sequence of partition satisfies, in particular if a sequence of partition Pn satisfies that the maximum length will approach to 0, this is equal to 0, this limit is equal to 0. Okay, this limit is equal to 0, and Tn and because for any partition we have a selection of points, so for this Pn let Tn be the selection of points. Let Tn is a selection of points, and Tn is a selection of points, for the partition Pn, then the limit of the Riemann sum, not lower and upper sum, but the Riemann sum that we have defined, just this limit and approach to infinity, or f Riemann sum with respect to the partition Pn, Pn for the selection of points Tn, this is equal to the Riemann integral of the function. Okay, this Riemann integral, it's just this is the common value of the actually upper and lower Riemann integral. So let me write it here, where we have defined the Riemann integral. So this is equal to so when we say this, and the common value is defined by and here, and this will be denote the common value of lower Riemann integral and upper Riemann integral. This is equal to the this is equal to the common value. Okay, this is equal to the common value of the lower and upper Riemann integral, because if they are same, they have the common value denoted by this integral. Okay, this is equal to I lower star of f, which is same as the I upper star of f. So in case f is integrable, it's the Riemann integral function, and the common value of the Riemann integral will be denoted by a to b, integral a to b fx dx, which is same as the lower Riemann integral as well as the upper Riemann integral. Okay, so this is the theorem. So first I will give an example where this the limit of the mesh of the partition will approach to 0. So let me explain first this. Let's take an example first here, so that you can better understand it. Let's take this interval. Suppose this is the interval, so 0, 1, and take this partition P, say Pn is this partition. It's 0, 1 by n, then 2 by n, so on. It's then n minus 1 divided by n, then it's n by n. Okay, then it's n by n, it's equal to 1. So this is the partition Pn. So what's the length of each subinterval is same. So here mod of Pn, which is the length of each subinterval. So that's equal to 1 by n minus 0, or 2 by n minus 1 by n, which is always equal to 1 by n. And you can easily verify this limit of mod of Pn, which is equal to limit of 1 by n, that's equal to 0. But limit is with respect to n, obviously, and approaching to infinity. So that's an example where you can see that the limit of the mod of Pn is approaching to 0. This is the sequence of partitions for P1. For if we choose n equal to 1, then the partition is 0 to 1. Okay, it is only 2 points 0 and 1. Then we have only one subinterval 0, 1. In case n is equal to 2, then we have partition 0, 1 by 2, 2 by 2, 0, 1 by 2, and 1. Then in that case we have two subintervals, 0 to 1 by 2 and 1 by 2 to 1. In case n equal to 3, we have 4 partition points and 3 subintervals, and so on and so forth. Now let's prove this theorem. Here f is integrable function. Okay, here f is integrable function. Proof of the theorem. Okay, so let's prove this theorem. Okay, now since f is a bounded function, so we can say this, since let's see we have bound of let's see belongs to R such that mod of f of x is less or equal to c for all x belongs to the domain. Domain is the interval a b. Now it's given that this f is Riemann integrable. So since f belongs to R of AB, so let's let epsilon be any positive number. Then we can find a partition. Therefore we can choose. It's the Riemann's criteria for Riemann integrable function is we can choose a partition. We can choose a partition P of A B. We can choose a partition P of A B such that this upper sum minus lower sum is such that upper sum minus lower sum with respect to this partition is less than epsilon. Okay, this is the Riemann's criteria for Riemann integrable functions, and here f is Riemann integrable. Now again we have this so also limit of mod of Pn and approach to infinity is 0. This limit is equal to 0. So if this limit is 0, then for each epsilon positive I can find some n naught such that this mod of Pn minus 0, obviously the limit is 0, is less than epsilon for all n greater or equal to n naught. And moreover, I choose n so large because it's the sequence of partitions that the mesh that length is approaching to 0. So it obviously means that the lengths of the subinterval will be approaching to 0. So we choose n naught so large such that the mod of Pn is less than the lengths of the subinterval of this partition. Okay, this particular partition. What is that? This partition, to the partition P, because it's a fixed partition. This partition P is here. So let me write this partition. It's equal to x naught x1 so on xn, which is equal to P. This is the partition P. This is a fixed partition. This exists here. So I choose, since mod of Pn is approaching to 0, that means the lengths of the subinterval will approach to 0 as an approach to infinity. So I choose n so large such that the length of each subinterval, or the maximum length for the mod Pn, is less than the length of each of the subinterval x0 to x1, x1 to x2, so on and so forth. So this can be done. So so here this is here. So since okay, this is I have done it here. I think where is the next page? Since limit of mod of Pn is equal to 0 and approach to infinity, so we can choose n naught so large such that mod of Pn is less than epsilon. But what's epsilon here? Epsilon I choose suitably here. It's equal to epsilon divided by 2c into m. So what's this m? M is here actually. Sorry, this m is here actually for the partition Pn. This is the partition of m points. Okay, this is m here. Okay. Okay, let me erase it first here. The last point is xm. Okay, last point is xm here. It's xm is equal to b. So that's m. That's our m here. And the maximum length and the mod of Pn is also, because it is approaching to 0, is less than the minimum of these lengths. Is less than the minimum of this x1 minus x0, x2 minus x1 so on xn minus xn minus 1. These are the lengths of the subinterval. It is xm, sorry, it's xm here, it's xm minus 1. Okay, this can be done because the mod of Pn is approaching to 0, and I have explained it how we can do it, how we choose and not so large with this property. Okay, this is true for all n greater or equal to n naught. Okay, so fix n greater or equal to, let's fix some integer which is greater or equal to n naught. Fix n greater or equal to n naught, and let's define the sequence Pn. Let's denote this Pn. This Pn is a sequence of partitions. Let's take this Pn is equal to, because this n is now fixed, so this will be the fixed partition. It's equal to, say, t naught, t1, so on up to t n. Okay, tk, sorry, it's tk here, not tn, it's tk here. Okay, it's tk, it's tk here. And let's make the following notations. Put capital MIP, it's the supremum of the function fx over the ith subinterval, but with respect to the partition p. With respect to the partition p, it's equal to supremum of f of x, where x belongs to the ith subinterval. Obviously, it's equal to, it's in xi minus 1 xi. Okay, and let's denote this capital Mi. It is the supremum of fx with respect to this partition Pn. F of x such that this x, it belongs to the ith subinterval of this ti minus 1 ti. Okay, here 1 is less or equal to I, less or equal to m, because it has m plus 1 points, and here 1 is less or equal to I, less or equal to k, because here we have k plus 1 partition points. And in a similar way we define small MIP. Okay, with respect to for the partition p, it's the infimum of f of x, where this x, it belongs to the ith subinterval xi, for 1 less or equal to I, less or equal to m, and that mi without p, it will be the infimum of the same function fx, but for the partition Pn, in the ith subinterval of this partition Pn. Okay, ith subinterval of this partition Pn, it's equal to infimum of x, where x belongs to ti minus 1 ti 1 less or equal to I, less or equal to k. So these are the notations which we have fixed here. Now we have this now we have 0 which is less or equal to integral a to b, which is the either upper Riemann integral or lower Riemann integral, because it is integrable, therefore they are equal, and this is the common value of the integral, minus the lower sum, obviously, because lower sum is always less or equal to the upper sum, so lower sum is always less or equal to the infimum of the upper sum, which is equal to the integral. So this is always greater or equal to the lower sum. Okay, so there is no confusion about this, but this one, because it's the infimum of the lower sums. So here I choose the partition Pn, okay, partition Pn, because for any partition Pn the lower sum is always less or equal to the integral. Actually lower sum is always less or equal to the upper sum for any partition Q. So that means this lower sum is always less or equal to the infimum of the upper sum, which is equal to the integral. Okay, so that's fine, and this is actually the infimum, so it's less or equal to the upper sum of the function f with respect to the partition Pn minus lower sum of the function f with respect to the partition Pn. Okay, now what is this? What is the supremum of the function f over the I subinterval with respect to the partition Pn? That's the capital Mi and the infimum with the small mi, and similar. So that means this is actually summation I runs from 1 to k capital Mi into xi minus 1 minus summation I runs from 1 to k small mi into xi minus 1, and that's equal to summation this I runs from 1 to n capital Mi minus small mi times xi minus 1. Okay, I will write this sum as v plus w, and I will explain what's v and what's w here. So this n is fixed here, note here this n is fixed here, its n is greater or equal to n naught. So that means for this n we have this, actually this mod of Pn is less than minimum of the lengths. Okay, so that means lengths of the subintervals with respect to the partition are less than this. So that means sum of the subintervals may contain in a single subinterval. Okay, because the lengths of those intervals are greater or equal to the lengths of the subintervals with respect to this partition. Okay, so on the basis of this I will divide this sum into two sums. Okay, for n greater or equal to n. So let's choose okay, this Pn. Okay, so let's go to the next page. Let's denote that sum by this is actually 0 less or equal to integral a to b fx dx, and this is less or equal to summation I runs from 1 to k. This we have done in the previous page, actually. So the next page, this is here. Okay, this is our sum, actually. This is equal to this here sum, and this is so this is equal to, I will write this sum as so let me first erase this. What's this here? Okay, so this is our previous page. Okay, this 0 is less or equal to the integral which is equal to this sum, and then I will divide this sum into two sums. I will write this as this is equal to v plus w. Okay, this sum is equal to v plus w, where v is the sum of the terms, where this capital V is the sum of the terms, is the sum of the terms, is the sum of the terms, is the sum of the terms. Obviously sum of terms of the sum are like this: mi minus mi into xi minus xi. It is those terms among of the sum such that, or for which this the interval with respect to this sum, which the I subinterval for which this interval is lie entirely in some subinterval of the partition P, in some subinterval of the partition P. Okay, and W, and this capital W, this W is the remaining sum, is the where this interval is not contained in any subinterval of the partition P, and W is the remaining sum, and W is the remaining sum. W is the remaining sum. Okay. Now we estimate these V and W separately. Now we estimate V and W separately. Now we calculate V and W separately. Okay, now we calculate these two sums separately. First we calculate V. First we calculate V. So what's V? Note that this V is equal. Note that this V is equal. It is certain sum. So let me denote this sum by it is summation 1 plus summation 2 plus what will be the, because we have at most case this summation with respect to M. Okay, why we have chosen M actually? Because this sum 1, what is this sum 1 actually? This sum 1, it is with respect to the interval T0 T1. Okay, suppose T0 to T1 it lies in some interval, say then this is sum with respect to that okay, this sum is of the terms of the sum. This is summation is the sum of the terms mi minus mi, ti minus 1 for each. This where this summation j in general, j runs from 1 to m, is the sum of the terms, is the sum of the terms, is the sum of the terms, terms are obviously these mi minus mi into ti minus 1 is the sum of the terms like this, is the sum of the terms like this, for which this ith subinterval ti minus 1 ti minus 1 ti lies in the j subinterval. Okay, lies in the jth subinterval. Okay, obviously this j varies from 1 to m because we have m subinterval with respect to the partition P1. So suppose for j equal to 1 we have x0 minus x1, then we have summation 1. Now what is summation 1? For this we have to find the subinterval with respect to the partition Pn which lies entirely in the interval x0 to x1. So suppose we have two subintervals, then we have then in this summation sigma 1 we have sum of two terms, and suppose we have three subintervals where it lies in the interval x0 to x1, then in the first sum we have three terms. And same for suppose j is equal to 2, then we have the interval x1 to x2. Then we need to find the intervals with respect to the partition Pn which lies entirely in the interval x1 to x2. Say we have suppose five subintervals, five such subintervals. Then the sigma 2 will be the sum of five terms, and this is so on and so forth. Okay. So this is obviously this j. That's why we have chosen here. We have chosen here this m sums, because we have m subintervals actually. Suppose first we choose the intervals with respect to the partition lying in the first interval, and then we choose intervals with respect to the partition lying which entirely lies in the second subinterval, and so on and so forth. We have m subintervals for the partition P. Okay, so this is so next we will then we try to calculate this sum now. But if this lies entirely in this interval, okay, because we are calculating V sum. But if the ith subinterval, if we have a situation like this, ti minus 1 ti, if it sits inside this j subinterval, then what happens? This one, the supremum of the function f with respect to the partition Pn over this interval is mi, capital Mi, but the supremum with respect to the partition this over the j subinterval is equal to mj. Okay, and this lies in this interval. That means the supremum mj is obviously greater or equal to this mi, and the infimum of this is greater or equal to infimum of this. So what it gives, that it will give us, so this gives this supremum is greater and this is smaller, and this infimum is smaller, this one is greater. So when I choose a minus sign, so we have this actually mi minus mi, because it is with respect to the partition Pn. The supremum is denoted by capital Mi, and the infimum is denoted by the small mi. It's obviously less or equal to, because supremum is it's mj here, but with respect to the partition P, and this is greater or equal to this, so minus term is this is less or equal to minus term is this. That's why this is here. It's mjp. It's true for all such. This holds. So also these are such intervals. If they may be one, they may be more than one, but the lengths of those subintervals will be less than the length of this subinterval, because each such subinterval is contained in the single subinterval. And that's here. Also the sum, also the sum of the lengths of those subintervals of the lengths of those subintervals, of the lengths of those subintervals of the partition Pn. Obviously they are the subintervals with respect to the partition Pn of the partition Pn of the partition Pn that lie inside, that lie inside this j subinterval cannot exceed the length of this interval. Never exceed never exceed this length. Okay, sorry, it's length here. Never exceed the length. Never exceed xj minus 1. It will never exceed this length. Thus we have the following. This summation j, this jth sum is less or equal to summation mj power p minus mj power p minus mj power p into xj minus 1. Whatever this sum will be, this summation j, it's not here sum now, because in this sum each mi is less or equal to mjp, and each small mi is greater or equal to small mjp. That, and then minus times small mi will be less or equal to minus times small mjp. So this is not sum, because you are summing here subintervals, the lengths of the subintervals, and that's less than the length this. Okay, so we don't need to write sum here. This is less or equal to this. This is trivial. So this summation j is less or equal to this. Therefore v, which is equal to summation 1 plus summation 2 plus summation m, and that's less or equal to summation j runs from 1 to m summation j. Summation j is less or equal to mj power p minus mj power p into xj minus 1. Okay, this is it. And this one, it's equal to, so you can see this is equal to s star, s upper star minus s lower star with respect to the partition p. Why? Because you can see it here, because this mjp and minus mjp, it is the or I can explain it here. I can write this as so this one, I will write it as it's equal to summation j runs from 1 to m mjp xj minus 1 plus, sorry, it's minus, then it's minus here, okay, it's minus summation j runs from 1 to n. I am breaking this sum as a difference. It's equal to mjp into xj minus 1, and this one it's equal to s upper star fp minus s lower star fp, and that one is less than epsilon, because we have chosen p a partial such that s upper star minus s lower star is less than epsilon, as f is integrable. Okay, this sum is less than epsilon. So thus our v is less than epsilon. Now we will show that the w, will show that this w is also less than epsilon.